you're comfortable with the material. What we did was paper chromatography. Now, paper chromatography is really fairly simple. Chromatography in general allows you to separate mixtures of compounds based on their solubility in the mobile phase, that's the liquid, and their affinity and interactions with the stationary phase. Now, every substance in existence has an inherent attraction for every other substance. Some of these will be very strong, some will be very weak. The stationary phase here is the paper. It's basically cellulose, and there are compounds that will interact strongly with the cellulose backbone, and there are compounds that won't interact at all. Likewise, our mobile phase here was aqueous ammonia, and there are compounds that are very soluble in that, and compounds that are not. So chromatography takes advantage of both of these things together to allow you to separate a mixture into the individual components. The stationary phase, once again, is the filter paper. This is cellulose, like I said, and the compounds will have an inherent attraction for it. The stronger the attraction, the slower they will move up the paper. The weaker, the further they go. The mobile phase was the ammonium hydroxide solution, and again, the more soluble it is, the further it'll go. The less soluble, the more it will stay down at the origin. So chromatography is just a balance of these two things. Now, when you do something like paper chromatography, you can quantitate exactly how far the various substances move by measuring what's known as an RF value. The RF value is simply the ratio of the distance that the spot traveled, that's your compound, to the distance that the solvent front traveled. Now, here is a little sample. This is where we spotted our stuff down here. Here's our little pencil line. So we started here. We let the solvent move up the paper. And when we shut it off, we made our little pencil line here, and that was our solvent front. Okay? So the distance the solvent front traveled here was a total of 6 centimeters. And as you see, this was a very nice separation. We got 4 different compounds out of our one spot. In order to calculate the RF, you want to measure the distance here for the solvent front. Like I said, that's 6 centimeters. It's where we started with our dot and where we wrote with our pencil when it was all over. The RF itself is simply going to be the ratio of the distance that the spot traveled to the solvent front. Just a simple ratio. That's it. So let's call this spot number 1. Spot number 1 traveled 5.5 centimeters up the paper. The solvent front traveled 6. So to do the ratio, our RF would look something like this. We would start off with the distance that our spot traveled. That's 5.5. Going to divide it by the distance the solvent traveled. That was 6. Do the division, and the RF is simply 0.92. Any questions?
Yeah, we're gonna do this at home.
Thank you.
There will be a problem very much like this on the lab report. Actually, the same image.
Right, I saw it,
Yeah,
but
okay.
I didn't print it because I thought it appears to me like we were gonna do it at home. Because it was saying it, and when you pull up the lab, it just come up to a test.
Right.
Right.
Okay. Now, paper chromatography, in spite of the fact that this seems to have worked nicely, really gives very, very low resolution. Way, way, way back in time, it was the best separation, the best way to identify mixtures of compounds, but chromatography has advanced a whole lot since then. I mentioned in lab the drug testing chromatography that is commonly used. This is a sample elution. This entire elution took, what, 4 minutes, something like that. Each of these peaks corresponds to a different substance in this mixture. This is called high pressure liquid chromatography. You have really a short column, but lots and lots of surface area. You pump your sample through at very high pressure, monitor it at different wavelengths, so you can detect different things. That's why these are alternate colors. And the separation is just phenomenal. The area under the peak air is directly proportional to the concentration of each of these things. You can even do better than that. You can link what's called mass spectroscopy with HPLC, so that as it comes out, it goes through a mass spectrometer that actually determines the exact mass of every compound. And so that gives you a really, really clear identification of what it is. Any questions? So go ahead and do your lab report number 3. Are we good?
So number 4 or number 3?
Number 4.
Okay.
Something like that. All right, let's go back to our first hour exam review. Again, if you have a sample exam you haven't turned in, please do it. Otherwise, here we go. What we're going to do here is simply go through every question on the sample exam. Now, the actual exam that you get is going to look physically identical to the sample exam. All the questions are different, but it'll look the same. Now, the whole point of that is so that you don't get some sort of freaking out when you look at the exam and say, oh my gosh, what is this? You're going to look at it and you're going to say, gee, I've done this before. I can do this. It's a very positive feeling, right? So we're going to go through each of the questions one by one. If you have questions about it, please ask. All right, question number 1. The mass of a sample is given at 5.5 grams, which in following properly expresses this in milligrams. Now, in order to answer this, I think the simplest way is to set up a given, a ratio, and a find equation. You guys that came in, if you have your sample exams, kind of pass them in or whatever. If you don't, don't. So our given here is clearly going to be 5.5 grams. So let's start off with that. There it is. The next, we need a ratio. Remember, the ratio simply describes how many milligrams there are in a gram. Milli, if you remember, was 10 to the minus 3. Now, we need to have a ratio with grams in our denominator. So we'll set it up like this. 10 to the third milligrams is 1 gram. Now, there's another ratio you could write that was just as good, but remember, grams must be in the denominator because we need them to cancel. Now, how many milligrams in 5.5 grams? Simply multiply this out, and you get 5.5 times 10 to the third milligrams. Think about it here. There are 1,000 milligrams in a gram, right? 1,000. We have 5 grams, 5.5 grams, therefore they're going to be 5,500 milligrams. Any questions? The second question. Oh, we've seen this kind of chart before. We're going to complete protons, mass number, charge, neutrons, electrons, etc. for a couple elements. Our first element here is magnesium. What you want to do first is find magnesium on the periodic table. Magnesium is over here in group 2, and there it is. Now, magnesium has an atomic number of 12. So we can start filling this in very simply. If its atomic number is 12, how many protons does it have? Atomic number is the same as the protons, isn't it? All right, let's look here at the charge box. In order to do the charge, you need to look at the number of protons and the number of electrons. Here we have 12 pluses and only 10 minuses. So we have 2 extra pluses, don't we? So the charge is simply plus 2. 2 extra protons. And finally, the number of neutrons. Remember that our mass number is simply protons plus neutrons, isn't it? So if we have 12 protons and a mass of 24, we must also have 12 neutrons. Any questions on that one? All right, let's find lead. Pb is lead. And it's down here, atomic number of 82. If the atomic number is 82, how many protons does it have? 82. Now, to fill in this box, we have to look here at our number of neutrons. It's given as 125. The mass number is neutrons plus protons, so you have to add these together. You don't need a calculator. 207. Now, we are given that the charge is plus 3. So that means it has 3 more protons than it does electrons. 3 more positives than negatives. If it has 82 protons, it must have 3 fewer electrons. So that will be 79. Now, I hope that you recognize this from the tutorial. Please, if you have any questions at all about this, do the tutorials. Any questions? All right, here we're going to take and write a formula for ammonium hydrogen carbonate. Now this requires you to remember a few of the very basic polyatomic ions. The only cationic polyatomic that we have is ammonium. And we remember that that's NH4. Carbonate is another polyatomic. This is an anion. Carbonate, I hope you remember, is simply CO3. Now this is ammonium hydrogen carbonate. So where the hydrogen is going to bring along with it a plus charge. So we have one plus here, one from the hydrogen. That'll neutralize both of these. So to write the formula, we need our ammonium. Here's our carbonate. And all we have to do is stick in the hydrogen. Once again, this is a question straight off of the tutorials. Please practice. Any questions? Our next one. We're looking for the atomic symbol of an anionic element. So it has a negative charge. It has 18 electrons, 16 neutrons, and a charge of -2. So first thing you have to do is figure out what element you're dealing with. Secondly, you need to remember that an atomic symbol has the symbol of the element. Then as a subscript in front, we'll have the number of protons. And as a superscript, we will have the mass number. If there's a charge, we'll put it afterwards. So, here's our periodic table. We have 18 electrons and a charge of -2. That means we have 2 extra electrons, right? So, we have 2 extra electrons, 2 more electrons and protons. How many protons? Simply 16. We're dealing with sulfur. So to write our symbol, we start off by making a big S. Number of protons, atomic number here, going to be 16 as a subscript. The mass number, well, we're given that we have 16 neutrons, we have 16 protons, that's going to be 32. And just to be nice, we're going to stick our charge here afterwards so that we know that this is in fact an anion.
I got a question.
Yeah.
Why do you put the mass number at the top on the left side instead of on the bottom of the S like it has it on our?
You know, I think that that's really cruel that people do that. When you look at the periodic table, the atomic number is always up top and the
Right.
mass is on the bottom.
Right.
So this is just a cruel trick that chemists do. Not my fault, but that's just the way it's done. Atomic number, mass number. So just look at your periodic table, flip it upside down.
Oh, I got it wrong. I got it upside down on my table.
Don't do that.
Bless you.
All right, our next one. Very, very simple density problem. We remember that density is simply mass divided by volume, right? We all know that. Here we are given a volume and we're given a density. Need to do a tiny bit of algebra. In order to get mass out, we're going to have to multiply volume by density. So our equation is going to look like this. To isolate mass, it's going to be volume multiplied by density. Now all in the world you have to do is substitute. Our density is 1.42. Our volume is 6.93. Multiply these together, and you get 9.84. Once again, this is a question straight off of the tutorials. If you have any doubts about them at all, just sit and practice them until you're bored to death. Okay? Our next one. Which of the following combinations is incorrect? So one of these is not like the others. This kind of requires you to know your basic polyatomics and know a little bit about the periodic table and ions. For example, aluminum. We look at our periodic table. I can find it. Here it is. Aluminum is here in group 1, 2, 3. It's in group 3. Remember, if you have a metal in group 3, it will form a +3 ion. So that's correct. Oxygen is here in group 6. It's a nonmetal. It needs 2 more electrons. So it's going to form a -2 ion, and we're going to call this oxide. So those two are right. Now our polyatomics. We have PO4, 3 minus, SO4 minus, and NO3 minus. First thing it should just jump out at you, because this is a common one we use all the time. SO4 is going to be a 2 minus, isn't it? So that's wrong. Not only that, this isn't persulfate, this is just something else. It's just wrong. Nitrate, NO3, 1 minus, PO4, 3 minus, this is phosphate. The one guy that doesn't fit is the sulfate. Remember, sulfate is SO4 with 2 negative charges. So review your table of polyatomics for the exam. Make sure you know the basics. Basics gonna be phosphate, sulfate, nitrate, maybe chlorate. Make sure you know those before you go in. Any questions? Significant figures. Everybody loves significant figures. Remember, when you look at a number and you're trying to decide how many significant figures, the first thing you do is say, does it have a decimal point? Well, yes it does. All right, so if it has a decimal point, the first rule is all the leading zeros disappear. They mean nothing. But the trailing zeros count. So for this number, we have an 8, and 3 trailing zeros. As I count, this is 1, 2, 3, 4. Trailing zeros count if you have a decimal point. They don't count if you don't have a decimal point. So make sure you understand that distinction. Once again, do the tutorial. Here we have a number in scientific notation. Now remember, scientific notation is kind of neat in terms of significant figures, because the rule is that all of the significant figures are in the coefficient. All of them. So all we have to do is count the number of digits in our coefficient. Here we have a total of five significant figures. Any questions? And let's do one more fairly simple one. Let's take a number and convert it to scientific notation. Here we have 0.00000013 meters. And we're going to write this in scientific notation. Now remember what we do here. We're going to start off with our decimal point, and we're going to move it so it's in between the first and the second non-zero digits. So the first two real digits. In this case, here's our number. We're going to move it from here to here. If we count, that means we're moving it 1, 2, 3, 4, 5, 6, 7 places, and we're going to the right. If you go to the right, our exponent is negative. If you go to the left, it's positive. So here we have a -7 for our exponent, and our number is simply going to be 1.3. Now, this is wrong because remember, none of these zeros are in our original number, so they don't count at all. Same thing with here. This is +7, and our answer is really -7. So look at these carefully. Once again, there's a whole tutorial on this. Spend some time and do it. Any questions? All right, well, let's do electrons. Everyone loves electrons. For silicon, use up and down arrows to complete this table. Step 1, you got to find silicon. So here's our periodic table. Silicon is here underneath carbon, and it's in group 4. All right, so what does that mean for electron configuration? First of all, it means that everything above it is full. It's all full. So every orbital above this is going to be totally full. Every orbital can hold 2 electrons, that's it. Therefore, the 1s, which would be here and here, is full. The 2s, that's this guy, this one and this one, it's full. Now our 2p's, we have 1, 2, 3, 4, 5, 6 electrons in the 2p's. They all show up as pairs. our third, our 3s. These guys are full too, aren't they? And now, our p's. We have 1, 2 electrons in our p orbitals. We remember they must be singles, and they both must be either up or down, but they must be the same. I always think positive, so I always put them up, and this is what we have. There will be a question just like this. It's going to deal with an element in the first 3 periods, just like this one did. If you have any doubts at all, please go to the tutorial and practice. Any questions? All right. Remember I told you that you needed a calculator and you needed to really love your calculator. The calculator on your phone isn't one that you're going to ever love. Don't use your phone. It'll be miserable. You want a calculator that you can enter scientific notation and get an answer out in scientific notation. Now, on the tutorial, we go through a method here that doesn't require a calculator. But the whole point of the tutorial, to be honest, is to make you fall in love with your calculator. So you can punch this stuff in, get your answers out, and be really happy with it. So the manual way, according to the tutorial, first thing you would do is simply multiply the coefficients. So 2.3 times 4.38, this gives us 10.1. Again, this is the manual method. Next, we're doing multiplication, so the exponents are going to add. So we have a plus 2 and a minus 12. So our exponent is minus 10. So the answer should be something like 10.1 times 10 to the minus 10. Now, unfortunately, this isn't quite in the standard format. Remember, we want 1 digit before our decimal, so we have to move this to the right one more. And when we do this, because we're moving to the right, it's going to drop this to 10 to the minus 9. But I really don't want you to sit on the exam and do this. I want you to take your calculator, punch in these numbers, and see the answer. Learn to use your calculator. We're going to use it a lot during the semester. Any questions? Everybody good with it?
I don't know how to get that 10 to the 9 on my calculator, but I can, you show me after class.
Okay, 10 to the minus 9.
I don't know how to do it.
All right, remember we talked about changes. Physical changes and chemical changes. A physical change simply is a change in what something looks like. It's some physical property. A chemical change, you're going from one substance to another. So, which of these would be descriptive of a physical change? Always accompanied by a change in state. So that's from like liquid to gas or solid to liquid. I mean, no, there are lots of things you can do physically just something that don't involve melting or boiling. I can take this ruler and break it in pieces. That's a physical change. And it's certainly both, or still, a solid ruler. So that's not right. Physical changes result in the formation of homogeneous mixtures. Well, that's kind of silly. A homogeneous mixture, remember, was a solution. Again, breaking the ruler certainly doesn't give me a solution, does it? Physical changes always produce new elements. Well, that would be fun. If I could drop this ruler and make gold out of it. But that's not going to happen. A and C obviously are not correct. In fact, none of these are. Remember, a chemical change gives you a new substance. Physical change is simply a descriptive thing about a particular substance. Here we go with nomenclature. We have P2O5. Remember, we have two groups of compounds that we deal with, molecular and ionic. An ionic compound will contain a metal. So remember, these are metals. A molecular compound will not contain a metal, only nonmetals and semimetals. So these guys in the corner here. This has phosphorus and oxygen. Phosphorus is there, right? And oxygen is there. Those are both nonmetals. This compound will be a molecular compound. Now, why do we have to figure that out? Because we have a slight difference in the way we name. If it's a molecular compound, we're going to use a multiplier. If it's an ionic compound, no multiplier. All right, this is molecular. We have 2 phosphorus. We have 5 oxygens.
See.
We would have to put a die here to represent the number of phosphorus atoms, and a penta to represent the number of oxygens. This has no multipliers. Neither does this. We'll skip C. This has no multiplier for our phosphorus, and this has no multiplier for the oxygen. The only one that works is diphosphorus pentoxide. Once again, there's a tutorial that will ask you these questions over and over and over again until you're sure of it. Any questions? All right, let's look at another compound here. Here we have copper 2 sulfate. Now let's think about this name first of all. Copper is right in there somewhere. I can't quite see, but there it is. It's a transition metal, isn't it? It's a metal. So this is an ionic compound. This says copper 2. Remember, when you have a transition metal, you need to show the charge on the metal, its oxidation state. And you do that with Roman numerals in parentheses right after the name. So this is copper 2. So our copper here has a +2 charge. Sulfate. Again, that's a polyatomic. We've memorized our basic family of polyatomics. And we know that sulfate is SO4 with 2 negative charges. So what we have here is a sulfate with a -2 and a copper with a +2. So you only need one of each, don't you? Therefore, copper 2 sulfate will simply have this formula. All right, so we've done this. How many oxygens are there? Well, that's not hard.
Or,
4. Any questions? All right, another density problem. This doesn't quite look like the table that you get in the tutorial, but the problem is still the same. We are given that the density is 0.841. We want to know the volume, and our mass is 58.3. So the first thing we do is we write down somewhere, density is mass divided by volume. Now in this problem, we are given the density, that's 0.841, and we are given the mass here, 58.3. So what you have to do is simply algebraically rearrange this to solve for volume. When we do this, our volume is simply going to be mass divided by density. Volume is going to be mass divided by density. So, in order to solve this problem, you simply need to take our 58.3 grams divided by our 0.841, and you get 69.3 mils. If you have any questions about how to do density problems, how to do these simple algebraic conversions, please visit the tutorial. Any questions? Now the next question asks you to do a Lewis structure. We're going to do boron trihydride. Remember, when we do a Lewis structure, first thing we do is find the elements in our periodic table. Boron is here in group 3. Hydrogen is here in group 1. That means that boron will have 3 valence electrons, and hydrogen will have 1. So we have 3 hydrogens with 1 each, and 1 boron with 3. We know that only 2 electrons can be in any one bond. So, start off with our boron, our 3 dots around it, the number of valence electrons. We have 3 hydrogens with 1 each. 2 electrons per bond. So we scooch them together. Going to convert these into line bonds now. And this is our Lewis structure. Remember that boron is an exception to the octet rule. It would dearly love to have 8 electrons, but it can only have 6. Everyone see that? There's actually a tutorial on drawing Lewis structures as well. I didn't assign that one. but if you have any questions, you can look at them. Some of the structures are more advanced than we typically do in this course, but nonetheless, it would be good practice. Another Lewis question. In a properly drawn Lewis structure, how many electrons are around the nitrogen in NH3? Now we just saw the boron wound up with 6 electrons around it. So we're going to see what happens with nitrogen. Again, here's our periodic table. Nitrogen is in group 5. Hydrogen in group 1. We have 1 nitrogen and 3 hydrogens. 5 electrons around the nitrogen, because it's group 5, and 1 each on the hydrogens. As always, 2 electrons per bond. So we scooch them together. And now all we have to do is count how many electrons are around the nitrogen. We have 1, 2, 3, 4, 5, 6, 7, and 8. 3 of these are shared with the hydrogens. 2 are just on the nitrogen. Again, our total is 8. Oops. That's supposed to turn colors. Any questions? This follows the octet rule. Remember, elements want 8 electrons because that makes them full and happy. K2O. What is its proper name? Just like the last one we did, step 1. Is this ionic or molecular? Well, where is potassium? It's right over there. It's a metal. If it has a metal, it's ionic. That means no multipliers, right? No multipliers. So, this is really simple. All we have to do is name the elements. K is going to be potassium. O is going to be oxide. So which of these works? Well, potassium oxide obviously works. We don't need to show potassium 1 because it's not transition. Dipotassium monoxide, nope, it's ionic. And dipotassium oxide, this is the correct name. Again, do the tutorial if you have any questions at all. And finally, which of the following compounds will the cation have a +3? Now, in order for a metal ion to have a +3 charge, what group does it have to be in? Ask yourself that. To have a +3, where does it have to be on the periodic table? Group 3. Group 3, there's no math in that. So here's our group 3 right here. So, calcium. Calcium's group 2. Magnesium, group 2. Ammonium, that's our polyatomic, and we know that's +1. Aluminum, by George, group 3. And phosphorus trichloride, that is molecular. Aluminum sulfide is the only compound. Now here in roughly 22 minutes, we have gone through all 20 questions, and I've talked a lot. On the exam, I'm not going to talk. You're not either. So you could actually even do it faster. Any questions?
How many questions is the actual exam?
The exam is gonna look just like the sample. There'll be 20 plus an extra credit. Okay? Exam is next Wednesday, so 1 week from now. Be prompt, bring a calculator, and what am I gonna say here? Do the tutorials. Now, hopefully this recorded, and I will put it up as soon as I can. On a real exam, if you wrote that, I would say fine. But, you know, realistically, that just makes sense. Two, one. Yep.